Hey guys, logarithmic functions. I promise you this time we're going to actually get into logarithmic functions. Last video was titled logarithmic functions and I got on a tangent. I'm glad I did it. I was going to bring that information in later, but sometimes when I've found it in teaching for as many years as I've taught that when material is tougher, sometimes it's better to just go ahead and get it out there and understand that there's going to be frustrations initially, and we'll just keep working and working and working. We'll keep looking on this, working on this stuff. So anyway, we're going to get into logarithmic functions. I want to start out by saying, my daughters are starting a little bit of algebra, and if they have something like this. Remember the good old days when you got to do something like this? And this, for 11th, or I'm sorry, for sixth graders and 11 years old, this can be a little challenging at first. But what I tell them is when you see something like this where you're adding 3, then just do the opposite. Okay? We have 3x equal 12. You're probably thinking, where in the heck is he going with this? Well, we're multiplying by 3, so let's do the opposite to solve the equation. So we're really doing the inverse. We're adding. To solve, we subtract. We're multiplying. To solve, we divide. Let's say we have x over 4 equal 10. We're dividing. Do the opposite. Multiply, but do it to both sides. Well, guys, it's kind of that theme of doing the opposite that brings in what we call logarithmic functions. And it turns out that the inverse of the exponential function is called a logarithmic function. So very, very, very important. The inverse of the exponential function is the logarithmic function. And guys, the key to understanding the relationship between exponential function and logarithmic function is to examine the equivalent forms. So in an exponential function, the form x equal b raised to the y power is the same thing as, or equivalent to, in logarithmic, is y equal log base b of x. Now, notice that when we have exponential function, the power that it takes to raise a base 2 to get x is the answer to the logarithmic function. So guys, logarithmic functions find powers that make exponential relationships true. All right, that's probably pretty crazy to you right now, but we know, for example, I think this is solidified better if we look at examples. Well, we all know that 3 raised to the second power is equal to 9. Well, this is equivalent to saying that the answer is the exponent to log base 3 of 9. So essentially, when you're focusing on logarithms, you're looking at, again, y equal log base b of x, and you're ultimately asking yourself, and I think this is the best way to think about it because I don't think our mind naturally thinks in logarithmic form, but I do think that our mind naturally thinks in terms of exponents. So we start with the base and we ask ourselves, what exponent would we raise our base to get the value that is right there? Now, let's first of all, let's just run through some converting exponential to logarithmic. Now, I know that log base 5 of 25 is equal to 2. Why? Because 5 raised to the second power is equal to 25. Base raised to the power equals this. I know that log base 9 of 3 is equal to 1/2 because 9 raised to the 1/2 power, which is the square root of 9, is equal to that value. I know that log base 2 of 1/4 is equal to -2 because 2 raised to the -2 is 1/2 raised to the +2, which is 1/4. So guys, logarithms solve for the exponent. So guys, let's well, I'll tell you what, let's go on. That I think that's good enough. All right, guys, let's find y on a few of these. Okay, let's go y equal log base 4 of 16. Now, essentially, what we're asking ourselves here is 4 raised to what power gives us 16? And guys, I think we all can see here that y would be equal to 2. It's pretty simple when our, well, I don't know about simple, but it's simpler when our exponent and bases and everything aren't fractions and aren't negative numbers. Let's go, oh, I don't know, let's find y or x. Let's go log base 2 of x equals -3. So what's that telling us? It's telling that our base raised to that power has to be the value we're looking for. Well, 2 raised to the -3 power is the same thing as 1/2 raised to the positive power. So guys, our answer here would be 1/8. Let's find when a b is unknown. So we have b of 100 equals 2. Now, guys, there's 3 parts here, isn't there? There's the base, there's the exponent, and there's the answer. Well, where's everything go? Well, the b has to go as the base. The answer is the exponent. And the 100, in a sense, is the answer to the exponential relationship. So what squared gives us 10? I'm sorry. What squared gives us 100? Don't you wish I'd do that on your exams? Mess up. Now, guys, there's a lot of properties for logarithms. And I'm not going to cover them all, but I'm going to cover the ones that are important to the goals of this class, at least as I see it. So some important properties of logarithmic functions. Well, guys, one important function is that the log base b of a product, and we'll just call this m times n, is the sum of the logs. Another one that you can probably take from this logically, I think, is that the log base b of a quotient is subtracting the logs. But guys, probably the most important property, for this reason I'm going to put a big star beside of it, the one that we run into, is that the log base b of a to the x power is equal to x times the log of b of a, log base b of a. So guys, what you see is when you have something raised to a power, you can bring this x out front and you get an equivalent statement. Now, when I saw something like this that wasn't intuitively clear when I was in undergrad many years ago, I always wanted to try it out. So let's just try out the first one. So let's go log base 10 of 3 times 2. And this is going to give us the opportunity to come in and talk a little bit about what it means to be log base 10. Now, on your calculator, if you come down and look at these two keys, you got the log key and the ln key. Let's get this to focus in a little bit better here. All right. Well, anytime we have log base 10, we use this key. Anytime we have log base e, we use the natural log key. Okay, so more about that in just a second. And these properties up here work with the natural log as well. So this is telling us that log base 10 of 3 times 2 can be rewritten as taking the log of 10, log base 10 of 3 plus log base 10 of 2. So let's try that out. So we've got the log of 3 times 2, which is 0.778151254. That should be the same thing as the log of 3 plus the log of 2, if this property is indeed correct. And you see it is. Now we can do a formal proof of that, but I think proofs are beyond the scope of this level course. Okay? 2, we can go log base 10 of 15 over 3. This is going to be log of 10 of 15, log base 10 of 15, minus log base 10 of 3. You guys, let's see if this holds true. So we can go log 15 divided by 3 And then we can go the log of 15 minus the log of 3. And we get exactly the same thing. Now the other property tells us that if we have log base 10 of 5 cubed, this will be the same thing as 3 log base 10 of 5. All right, let's give it a shot. Log 5 raised to the 3 power and 3 log of 5 gives us the same thing. Now guys, that last property is going to be extremely important. Now guys, is similarly speaking to the ones that we just did. When we have log base e of anything, this is written as the natural log of anything. Okay, so if we have a 5 there and a 5 there, those are the same things. And let me prove that to you. Well, no, I can't prove that to you. So guys, anytime we have, well, I can, but I'm not going to at this point. We need to get into something a little different here. So if I have base e, we use the natural log key. So, but the properties hold the same. If I have the natural log of AB, then this is the natural log of A plus the natural log of B. If I have the natural log of A divided by B, then this is the natural log of A minus the natural log of B. And if I have the natural log of, let's say, A raised to the B power, then this can be rewritten by bringing the B out front and taking it times the natural log of A. So an example, the natural log of 8 times 4 should be equal to the natural log of 8 plus the natural log of 4. So that should be the natural log of 8 plus natural log of 4. Same thing if we divide. So what I can do is the natural log of, for example, let's just go 8 divided by 4. So that should be the same thing as the natural log of 8 minus the natural log of 4. Same thing. And when we get a power, for example, for this, if we take the natural log of 2 raised to the 1/2 power, then this should be the same thing as 1/2 times the natural log of 2. So I can take the natural log of 2 raised to the 0.5 power, which is going to be equivalent to 0.5 times the natural log of 2. Okay? Now, so guys, in a nutshell, this relationship between e's and 10s and so on and so forth, okay, we can say that log x equal y is equivalent to what? Base 10 raised to the answer equals x. The natural log of x equal y is equivalent to what? Base e raised to the answer equal x. So when we put in our calculator something as simple as log of 32, what is this telling us? Guys, log, think what? Base is 10. 10 raised to some power is 32. So this would be y equals log 32. Says that the base is not up for debate. When we have a log with no number there, it's given to be base 10 raised to the answer equal 32. So guys, what we can do here is we can go the log of 32 is 1.505 because 10 raised to that number is 32. Same thing we get, y equals the natural log of 18 is telling us without question base e to that answer equals 18. So guys, when I put in my calculator natural log of 18, we get 2.89037 blah, 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 because, guys, your E key is right there. E raised to that answer is going to be what? It's going to be 18. That's what it does. So guys, logarithms undo exponential functions, and because the exponent contains the variable, when it undoes, when it's the inverse of it, it finds the exponent that makes our relationship, that makes our equation a true statement. Now, I told you earlier that we needed to think in bases in terms of three ways, okay? And it should make a little bit more sense why I said that. So bases, all right? Base 10. This is important because that is your log key. Base E. That's important because that's your natural log key. What happens when the base is anything other than 10 or E? Well, that's where we get into what's called the change of base theorem. And the change of base theorem just simply says that if we have log of any base b of something raised to, say, the x power that x can be found by taking the log of b over the log of a, or the natural log of b over the natural log of a. Yeah. Okay. Let's work some problems. Now let's keep bases. These types of problems look like this. 10 raised to the x power is 51. Base is 10. No brainer. Log key takes care of this. So the solution is simply to put in your calculator log of 51. Out to 4 places, which is usually what your my math lab will require you to do. So 1.7076. This is a true statement because 10 raised to that number gives you 51. The other type of problem we run into is when our base is e. E to the x equal 11. No brainers, natural log. So all we have to do in this problem is just put the natural log of 11 in our calculator, and we will find the power that e has to be raised to get 11. We can check that by going e raised to the answer of the previous problem, and of course it's going to be 11. The fun happens when we get something raised to a different base. So what happens when our base is not equal to e or 10? For example, what if we have 3 to the x is 141? What power would we raise 3 to get 141? Well, I know that 3 raised to the 4th power is 81, and 3 raised to the 5th power is 243, so I know it's going to be somewhere between 4 and 5, so x is going to be 4 point something, but what is it? Well, I could do trial and error. That's a little pretty close. That's a little bit closer. A little closer. Ooh, a little closer. You know 4.6 is going to be too much. So it's going to be somewhere between 4.5 and 4.6. All right, somewhere between 4.5 and 4.51. Guys, we can get it precise. We don't need to do all that trial and error stuff. We can get it precise. So the way we do that is with the change of base theorem. And the change of base theorem just simply says that x can be found by taking either the log of 141 over the log of 3 or the natural log of 141 over the natural log of 3. Either one of those. So let's try them both out. So the log of 141 divided by the log of 3 versus the natural log of 141 divided by the natural log of 3. It's going to be weird. These are going to be the same thing. And in both situations, if I take 3 and raise it to that value, well, lo and behold, what am I going to get? I'm going to get 141. Because that solves the problem for me. Now, sometimes we get a little bit more information in there. Sometimes it gets a little crazier. And, we get things like, I don't know. Let me see if I can find something that'll be tons and tons of fun. Let's say that we've got something like, I don't know. let's say we've got 10 times 8 raised to the x power is 417. This is pretty easy, actually. Well, to be able to apply the change of base theorem, because again, it's called the change of base theorem because it's base 3, but we can take log base 10 over log base 10, and again, we just change the base to either 10 or e using this technique right there. But what we would do here is we would first of all just divide both sides by 10 and isolate the term that has the exponent, the variable, just as we would do otherwise. Now what's going to happen? Change of base. Either one you want. I'm going to do the natural log. So the natural log of 41.7 over the natural log of 8. And we get 1.7939. So let's see if that works. Let's take 8 and raise it to that value. Multiply by 10. And we get 417. All right, guys, this is it's pretty cool stuff, I think. Maybe you're not impressed just yet, but I don't know. I think it's kind of cool stuff. It's very powerful, especially when we're trying to undo certain things. All right, give you a couple of problems here to see if you can figure them out with me. Put what's that mean? How would you solve that? First of all, what's it mean? I know what it means. Do you know what it means? Well, guys, even as long as I've been doing this, and you know, as much as I feel like I know about math, I mean, pales in comparison to some people, but more than most, more than many. I look at that, I still have to think about that in terms of exponential form. It's kind of like someone, you know, my daughters are from China, and we ran into a lot of people who are Chinese, or even people who are just from foreign countries and speak a different language. Their first language is something other than English. And they will say that when they think in their original language, their first language, and then they translate it into English. They don't think in English, they translate it into English. Well, guys, I don't think in this. My first language is exponential form. This is a second language to me. So what I would do here is I would understand that if there's no base there, it's base 10. This is the answer to the exponent. And that's what this is equal to. So guys, this is as simple as just putting 10 raised to the 1.212 power. I think that's what I said, right? Yeah. Which is 16.2929. Well, 16.2930. If we go to 4 places. I can't remember whether my math lab goes to 4 places or 5. But, you know, whatever it says, just go for it. What about this? What would you do to solve this? What's the base? Something other than 10 or e, right? So now, let's see if we can learn from a previous problem. When we had 3 raised to the x power equals like 15, for example, x was equal to the natural log of 15 over the natural log of 3. Change of base. Again, this base isn't 10 or e, is it? Something else. So we use the change of base theorem. So how do we apply this? What role does the 3 play? That plays the 1.005, right? What role does the x play? Well, that's replaced by 2x, so we got a little bit more work to do. And this 3 over here is the 15. So it looks like to me that we're going to have the power, which is 2x brought out front. And we're going to have the natural log of 3 over the natural log of 1.005. But when I get this answer, I have to divide by 2. Now, there's a lot of stuff going on here, so I'm going to go baby steps. So natural log of 3 divided by the natural log of 1.005. And then I'm going to divide that by 2. So my answer is 110.1357. Now, guys, I don't know about you, but I feel like I need to check that. So let's check it. Let's go back to the original problem. Okay, my x is 110 point, or at least proposed to be 110.1356. I need to multiply that by 2. 1.005 raised to that value better be, well, simple 3. And it is, so I believe that our answer is correct. I know our answer is correct. I don't even have to believe it. Guys, one more and we'll be done. Let me see if I can come up with something that's really fine and dandy. I don't know. Let's go. Natural log of x equals negative 1.8879. All right, guys, that's Chinese. Well, I can't even say that because Chinese isn't my second language. But that's not my first language. It's just not. My first language is exponential form. The LM part tells me that the base is e. In logarithmic form, this number is the answer to my exponent. And the number right there is the answer to the exponential form. So gang, all I got to do is put e to the negative 1.8879, and I got my answer. Now, are we sure that's right? Well, the original problem is the natural log of what our answer is needs to be negative 1.88, so let's just do it. The natural log of the answer that we just came up with is indeed going to be exactly what we need. All right, guys, I'm tired of messing with you, probably bombarding your brain, driving you crazy. We're going to spend 2 whole weeks on this stuff. So if it's a little fuzzy to you, if you're struggling just a little bit, it probably means nothing more than you're normal. hang in there, and assignment's been posted, so or at least I think it has, and so get that in by the due date. Bye.